In Prolog, all data are represented as terms, and we can write some terms in different ways. For instance, a string is written in double quotes. An example is the string Prolog. And the meaning of a string depends on the Prolog flag double quotes. If the flag's value is chars, then a string is a list of characters, that is, one character atoms. On the other hand, if the flag's value is codes, then, as the name suggests, a string is a list of codes. So it's pretty clear that setting the flag to codes isn't very useful, because if we only see such character codes in answers, then, to be honest, we have no idea which characters they stand for, and this makes answers very hard to read. This means that chars is really the only value we need for this flag. And especially in more recent Prolog systems, such as Tau Prolog and Scryer Prolog, chars is already the default value. And this is one of the features that makes these systems very usable and pleasant to work with. And if chars isn't yet the default value in your system, then I highly recommend you enable this in a configuration file. So we can say a string is a list of characters, that is, one character atoms. At least this is the direction where Prolog systems should be moving, to make answers conveniently readable. And of course, lists are a great representation for many use cases, because Prolog is very well suited for reasoning about lists, and it provides many built-in mechanisms for it. Most notably, Prolog has a built-in grammar mechanism called definite clause grammars, or DCGs for short, which are ideally suited for parsing and describing lists. However, there's also a significant drawback to lists, because lists are a very inefficient representation of strings. For instance, for ASCII strings on 64-bit systems, lists incur a 16-fold or even greater overhead. And that's, of course, a significant disadvantage of lists. Now, why does this happen? To see this, let's consider an example. Let's take the string ABC. And as we said, this is simply a different way to write the list with 3 elements, A, B, C. And this list in turn is simply a different way to write a certain compound term with principal functor dot and 2 arguments, right? So if this string occurs in a Prolog program, then it means that this compound term must be somehow represented in memory. And of course, there are different ways to do this. And the way this is stored in memory depends on the Prolog system. However, it's pretty safe to assume that the functor of the term must somehow be stored, for example, as a tagged value or as a pointer to an entry in a functor table. So we assume there's a location in memory where dot/2 is stored or referenced. And in Prolog implementations, such a storage location is also called a memory cell or simply a cell. And the arguments of the term must of course also be stored. Well, in this case, the term has 2 arguments, and so the following 2 cells store these arguments. So the first argument is the atom A, and so the next cell stores this atom, using, for example, a pointer to an atom table. And the second argument is a compound term. And so we apply the same idea to store this compound term. First, the principal functor is again dot with 2 arguments. So the functor is stored, and the following cells store the term's arguments. Namely, the first argument is the atom B, and the second argument is a compound term with 2 arguments, the atom C and the atom nil, and that's it. So this is a common way to store this compound term, by simply storing for each subterm the functor followed by the arguments. And functors and atoms are represented by pointers to table entries. So what we can say from this is that representing a list with n elements takes at least 2 times n memory cells. Because for each element that occurs in the list, we need to represent the functor dot and the element. And in fact, in some Prolog systems, it even takes 3 times n cells. because what I show here is, in a sense, already an improved way over the naive way of storing lists. Because if we represent lists naively, this means that the second argument of each list cell is a pointer to another compound term. And so we would need 3 cells per element. Now, a twofold or threefold overhead doesn't seem too bad, right? However, the main overhead of this representation is due to the fact that these memory cells are byte aligned to ensure fast access. And so on 64-bit systems, one memory cell takes 8 bytes. And that's of course a huge overhead. So what we want instead is a much more compact representation, ideally with 1 byte per character for A, B, and C. And the really great news is that there's a way to get this, or at least to get something really close to this. Because, of course, we still need to indicate the end of a string. And, of course, we also want to be able to represent partial strings. That is, lists of characters where the tail is a variable. So, here's an efficient representation of strings. And I mean, of course, an efficient internal representation. So this is something that the Prolog system must do for us behind the scenes, because we simply write a string and we expect the Prolog system to represent the string efficiently internally, while to us, as Prolog programmers, the string appears as a list of characters. So first, the Prolog system should represent strings as sequences of raw bytes in memory, using, for example, UTF-8 encoding, which contains SK as a subset. And 0 terminates a string. Then up to 7 additional zeros may be used for padding. This is to keep the cells byte aligned for fast access. And then the next memory cell is one of the atom nil to indicate a complete string, or a variable to represent the tail of a partial string. That is, a partial list of characters, where further elements can be appended by instantiating the tail, or a pointer to a string or a partial string in this representation, or the list constructor dot/2, which is needed for strings where 0 occurs as an element. And that's all. So how does this work exactly? And for illustration, suppose the Prolog system provides a predicate like chars_list with 3 arguments. Chars list of C's ls0 and ls is true if and only if the first argument C's is a list of characters, and C's is the list difference between ls0 and ls. Because if we have a predicate like this, then we can reason about partial lists of characters in this efficient representation. And this means that we can efficiently concatenate strings. So I now suppose that our Prolog system makes such a predicate available. For example, let's say we want to represent the string ABC as a list difference between ls0 and ls, where ls is the tail of the list ls0. So we simply write the string ABC, and now the Prolog system must internally represent it efficiently, in the way outlined above. So the system needs to allocate a memory cell, which on a 64-bit system means 8 bytes. And now the string can be stored in this cell as a sequence of raw bytes. So if we are using UTF-8 encoding, then the system can simply store the string as A, B, C, using the first 3 bytes of the cell. And then 0 terminates the string. And further zeros are used for padding the cell. And in our case, the tail of the partial string is ls. And so the next memory cell is simply the variable ls. And to repeat, all of this happens completely internally. And to us, on the Prolog level, this simply means that ls0 is the partial list with elements A, B, and C, and tail ls. And if we use, for example, the atom nil instead of ls, then this means that ls0 is the list with elements a, b, c. So this is an example of a complete string, and this is indicated by the atom nil in the next cell. And as mentioned, the great advantage of using a list difference is that we can efficiently concatenate strings. So, for instance, if we state that the tail of ls0 is ls1, and in addition to that, we demand that the string de is the list difference between ls1 and ls2, then this can be efficiently represented, because this means that ls1 is a pointer to a partial string. And that string again contains raw bytes, in this case d and e, terminated by 0, padded to the next cell, and the next cell is the variable ls2. So the Prolog system does this internally, and as a result, the partial list ls0 now contains the elements a, b, c, d, and e, and the tail is ls2. So in total, this means that we can very efficiently append elements to a string by instantiating the tail. And this allows concatenation that's independent of the length of the first string. So we benefit from the usual advantage of using list differences. And this also means that files that don't contain 0 bytes can be simply mapped directly into memory with the system call mmap. And only the end of the byte stream needs to be slightly adapted to form a string in this representation. So in memory, we only need to insert 0 and nil at the end, and we have a valid string in this representation. And as a consequence, library PO for pure IO becomes very fast. And moreover, strings and files that contain 0 bytes can be represented too. For instance, suppose we have a list with the characters A, B, followed by the character corresponding to the character code 0, and then the character D. And this list of characters shall be the list difference between ls0 and ls. So ls is the tail of the partial list ls0. Then clearly A and B can be easily represented as the first 2 bytes in a cell. But now we can't directly represent the byte 0, because in our representation, 0 terminates a string. So we use a workaround to represent 0. First, we terminate the string using 0, and if necessary, we pad the cell with zeros. And now, to represent a 0 byte that occurs in the string, we use a list constructor, and its 2 arguments are, first, the character corresponding to character code 0. So this is how we represent 0 as an element of the string, with its own list constructor and memory cell. And because 0 bytes are very rare in text files, if they occur at all, this overhead is completely acceptable. And then the second argument, so the tail of the list, is a pointer to a partial string, which points, for example, to the next cell. And in that cell, we start a new string for the remaining elements. So in our case, this remaining string has a single element, D. And then, as usual, we terminate the string with 0, pad the cell, and the next cell is the tail of the partial list, so the variable ls. And on the Prolog level, ls0 is simply a partial list with 4 elements and tail ls. So, of course, this representation happens completely internally again. And Prolog programs and application programmers don't see it at all. So, in summary, this representation gives us everything we want. It allows us to conveniently reason about strings as lists of characters, using built-in mechanisms like DCGs. And at the same time, the representation is extremely compact. with very low overhead, if any at all. And that's of course great, because Prolog was in fact designed for natural language processing, and an encoding of strings that's convenient and efficient is of course important for processing text. So if your Prolog system doesn't yet implement this representation, ask your vendor for it. And say, for example, please, it's been 50 years. And now we want to use Prolog for the use cases it was designed for. So please implement strings efficiently. And at the same time, please let us use DCGs and other built-in features to reason about them as lists of characters. So, as Prolog application programmers, even if we don't implement a Prolog system ourselves, we have a responsibility and can to some extent influence how Prolog systems are developing. And so we can, for example, use and also promote Prolog systems that already implement strings in this way, and hope that over time other systems will follow their example. And of course, for implementers, it's not so easy, because first they need to understand this representation. And then they need to design or adapt their systems so that all built-in features, such as unification, treat such strings in the intended way, as lists of characters. And of course, a system's garbage collector must also take this into account, so that, for example, a substring isn't mistaken for a pointer to another cell. So strings may need to be allocated in their own memory region, where the garbage collector works differently. And however difficult it may now seem for implementers, such a representation will be well worth it in the long term. And it will enable new use cases for Prolog that are currently out of reach. For example, this representation makes Prolog easier to teach than, for example, using poorly thought out ad hoc representations for strings or raw bytes. Because it's very easy and convenient, and also standard conforming, to work with strings as lists of characters. And at the same time, it's automatically efficient if strings are implemented in this way.